Okay, so welcome once again, one and all. So, in this lecture, we will discuss the consistency. Okay, so in previous lecture, means lecture number two, I stated that or discussed that for a good estimator, there are some characteristics. The first characteristic was unbiased estimator. And now here it is the second characteristic for a good estimator, that is consistency, means our estimator should be consistent. Now, actually, this one, first one that you are seeing on your screen means up to here. Oh, sorry, up to here. This is the basic definition of consistency. Okay, that what's the meaning of an estimator? That it is a consistent estimator. Now, this definition actually it is in terms of stochastic convergence. The word is stochastic that I have used, stochastic. Okay. So, stochastic convergence, this is actually convergence in probability. What is a stochastic convergence? It is convergence in probability. Okay, so here P stands for probability. Okay, so actually we say that an estimated Tn, Tn, it is a consistent estimator of parameter gamma if Tn converges to gamma in probability. Okay. So in other words, that Tn converges to gamma stochastically as n tends to infinity. Okay. And this stochastic convergence or convergence in probability, its definition is this one. Okay. Now, this definitions, okay, these definitions or even stochastic convergence, they are beyond our present lecture series. So, we will not discuss consistency according to the basic definition of definition, but we will discuss consistency according to the sufficient conditions for consistency. I repeat, since these definitions they are a bit beyond our scope of present lecture series, so we will discuss this consistency according to these sufficient conditions, not according to the basic definition of consistency. Now, these sufficient conditions, they tell us that suppose Tn, let Tn be a sequence of estimators. So first of all, what is Tn? So Tn is a function of sample observations. Okay. So this I had already discussed. Now, what will be T1? So obviously, it will be nothing but this. What will be T2? It will be nothing but x1, x2. And then T3, it will be nothing but T3, x1, x2, x3, and so on. Means T1, it will be having only one sample observation, x1, means it will be a function of single sample observation. Wait, please. Yeah, sorry. And T2, it will be a function of two sample observations. T3, it will be a function of three sample observations going on. So ultimately, we are getting a sequence. You can very well see, one can very well see that we are getting a sequence of estimators. Okay. So earlier, we were stating that this Tn, it is an estimator. Now he is stating that this is a sequence of estimators. Obviously, both the terminologies are same. There is no both the terminologies are valid. Okay, because if I put n 1 2 3, then obviously I will get a sequence of estimators. Now, if expected value of Tn, if the expected value of Tn, it approaches to gamma, and variance of Tn, it approaches to 0 as n tends to infinity. So if this happens, then we say that Tn is a consistent estimator of gamma. If expected value of Tn, okay, so expected value of Tn, it approaches to gamma, okay, it is gamma, please mind, okay, and variance of Tn, it approaches to 0 as n approaches to infinity. Then we say that this Tn, it is unbiased estimator of this, sorry, it is, sorry. Then we say this Tn, it is consistent estimator of this parameter gamma. Okay, wait, please. Yes. Okay. Now, what's the meaning of this that n tends to infinity? Actually, here n is sample size. So, if we say that n tends to infinity, then we mean that this sample size becomes large enough or sufficiently large. What's the meaning of n tending to infinity? It means that your sample size is becoming large enough, or it is becoming sufficiently large. Okay. So as our sample size grows, then if expected value of Tn tends to gamma and variance tends to 0, then we say Tn is consistent estimator of gamma. Okay. Now, although how we get these sufficient conditions, it has a proper mathematical approach. But just one, if I give you a rough idea, okay, not 100% mathematically correct, okay, but just a rough idea to understand that how we can have these conditions for a consistent estimator. So actually, I am having just wait, yeah. So here this is one. So if I write here, it is mu equal to say 15. Okay, so here it will be say student number 1. Okay, then I have this is one more. Say even here mu is 15, student number 2, and again here say here mu is 15, and this is student number 3. So now here, if I say here I have say 14, then here I have 13, then here I have 12, here say I have 16, 17, and 18. And here say I have 14, here say 14.2, even here say 14 point, say 3. And here say I have 16 and say 15.3, and here it is 15.2. And here what I have, say here it is 16, and here say 21, here say 17, here say 20, here it is 18, and here it is 19. Okay. What is this mu 15? First of all, what is this mu 15? Actually, this is the average marks of any population of students, okay, in a given exam. So what is this mu? This is average, okay, average marks of a certain population, of a certain population of students. Okay. So this population of students, it can be of any, suppose it can be any institutes, student population, or a group of institutes. Okay. Means that this is population of students in New York, in Delhi. Okay. So it can be any large population of students. Now, uh, if I ask you that, tell me which student you feel, I repeat, which student you feel is more consistent or most consistent about mu 15. Okay. Then here, what are these? 12, 13, 14, 16 means whatever I have marked these. Actually, these are the marks of student. For example, what are these? 12, 13, 14. These are marks of student number one in 6 exams. Okay. And what are these? These are the marks of student number two, again in six exams. Okay, and obviously this mu 15, this average marks, it is based upon these 6 marks, 6 exams. Okay, and even here, these are the marks of student number three in same 6 exams. So based upon these 6 exams, this mu 15 has been calculated. Okay, now which student is most consistent about mu 15? Which student is most consistent about mu 15? So, as per my gut feeling, I think you will answer that student 2. Student number 2 is most consistent about mu 15. Uh, First of all, why student 3 is not consistent about mu 15? Actually, expected value of M3. So what is M3? The marks of third student. M3, the marks of third student. It's expected value. Expected value means average value, mean value. Actually, it is tending towards almost say 18 or 18.5. Okay, the expected value of M3. So once again, this is just a rough idea. It is not 100% mathematically correct. Okay, so this is just a rough idea to understand these conditions. Okay, rather than merely cramming. Now, the average marks, okay, of third student, they are tending towards 18.5. How? Actually, you add all these marks, you add these and divide by 6, you will feel that expected value is tending towards 18.5. So, but we were interested about 15. So, expected value of M3, the marks of third student, it doesn't tend towards 15. So that's why the third student is not consistent about mu 15. Yeah, it may be consistent about 18.5, but here I asked about 15. Now, student number 1 and 2 means if I say that expected value of M1, okay, the expected value of marks of student 1, yeah, it is tending to 15, okay, and expected value of marks of student 2, okay, even it is tending towards 15. How? If you take the average of these marks or these marks, obviously it is getting closer and closer to 15. Okay, the average of these 6 marks, okay, means sum of the marks divided by 6, it is getting closer and closer to 50. But for this student, student number 2, this distance, if you see, this distance, actually, what is this distance? Actually, this distance, it is the measure of this distance, it is the measure of the standard deviation. Okay, actually, how we define standard deviation? That yes. So standard deviation of any random variable x, it is square root of variance of x, positive square root of variance of x, and so this is for the expected value of what? X minus expected value of x whole square. Okay. So means what is standard deviation? It is a measure of this difference x minus ex. So what is x here? Here in this example, this x, it is our marks. Okay. And what is expected value of x? It is the average of marks, mean of marks. So here, what is the mean of marks? It is 15. So what is this distance? This distance, actually it is nothing but this as 16 x, and 16 its difference from its distance from 15. Similarly, what is this distance? Okay, even this distance, it is the distance of 15.3 x. Okay, our x. Even here, this is x. So distance of our x from its mean value, this mean value, expected value. Okay, and similarly for this. Okay, now actually this is a measure. Standard deviation measures this. That's why it is deviation, standard deviation. Okay, so this distance, it is the measure of standard deviation. Now, for this student, the standard deviation of M2 means the marks of second student, it is becoming smaller and smaller and smaller. One can very well feel that standard deviation of marks of student 2, the standard deviation of marks of student 2, they are becoming smaller and smaller, means this distance. Okay. So if standard deviation is tending to 0, what about variance of marks of student 2? Obviously, it will be tending to 0 because variance is nothing but the square of this. But for first student, this standard deviation, it was not, it was not tending to 0. Rather, for this student, this distance, which is a measure of standard deviation, okay, this distance is becoming larger and larger and larger. Wait, please. Yeah. So that's why we say that student 2, it is most consistent about mu 50. Now, here, if you go back to the our definition, so instead of marks, what we have means here marks, we are using MI, M1, M2, M3. But we have TN. Okay. And what was the parameter here? Here parameter is mu, and here it will be any parameter, gamma. Okay. But for us, as I already told you in the previous lectures, that our usual parameters, the usual unknown parameters, which is to be estimated, which are to be estimated, it is either mu or sigma square. Either it will be population mean mu or population variance sigma square. Okay. Now, this is a suggestion that one should take a pause for this question, and he should try to answer this question of his own. Why so? Because the answer of this question, it lies within our previous discussion. Okay, so in the previous discussion means in the first lecture or okay this lecture, it is sufficient to answer this question. Now here, sample mean. We already know that sample mean is unbiased estimator of population mean. Okay. Uh, but from here, I can say that expected value of x bar, it also tends to mu as n tends to infinity. Why so? Actually, this equation, it is giving us a constant sequence. Actually, what is your x bar? It is x1 plus x2 plus xn divided by n. This is your x bar and this is mu. Okay. And when we proved this result, when we had proved this result, we didn't assume any restriction for n. our sample size. When we proved this, okay, in previous lecture, we didn't assume any restriction for n sample size, that n can be only 100, it can be only 1000, million, billion, whatever. Okay, means if n is 10, if I say the sample size is 10, what will be this expectation? It will be mu. And if n is 100, what will be this expectation of this sample mean? Again, it will be mu. And if n is 1000, again it will be mu. Going on. Means if your n is tending to infinity, your expected value of x bar, even it will be tending to mu. Okay. It is just like that suppose if I give you this sequence, say an, which is nothing but say 1 by n, okay, say n from 1 to infinity. So this is actually 1, 1 by 2, 1 by 3 going on, okay. So put n 1, 2, 3. So this sequence, it tends to 0. An, it tends to 0 as n tends to infinity, because this sequence, it is becoming smaller and smaller and smaller, the terms of this sequence. But if I give you this sequence, say a constant sequence, say I give you 3 and 1 to infinity. So what will be the first term? 3a1. What will be the next term? 3a2. Next term 3 going on. Okay. Here, what is the first term? 1. Okay, this is the second term, third term, and so on. Here, first term, second term, third term. Now, if n is 100, here if it is 100 term, what will an? What will be an? 3. Okay. And if n is 1000, what will be an? It will be again 3. Okay. Means here, n is whether it is 100, 1000, million, billion, your sequence will be still 3. But here, if n is standing, if n is 100, then what is your sequence term? It is 1 by 100. But if n is 1000, what is your sequence term? It is 1 by 1000. Means here, an is becoming smaller and smaller and smaller. So, an tends to 0 here, as n tends to infinity. So, even here, so what is the case here? That our sequence is constant. So, even here, our sequence is constant. So as n tends to infinity, expected value of x bar, it will tend to mu. If, I repeat, we already know that expected value of x bar is equal to mu or sample mean. This is unbiased estimator of population mean. But this will imply that expected value of x bar, it also tends to mu as n tends to infinity. Why? Because it is ultimately giving us a constant sequence. Variance of x bar, that is equal to sigma square by n. This I had proved in previous lecture. Okay. And this tends to 0 as n tends to infinity, obviously. Okay. Because this is becoming larger, so this term will become smaller and smaller. So what we have proved, that expected value of Tn. So what is our Tn here? X bar, the function of sample observation. It is tending to what? Gamma. So what is our gamma here? Mu. And variance of Tn, x bar, it is tending to 0 as n approaches infinity or as our sample size grows. Okay. So what does it prove? It proves that sample mean, okay, sample mean, it is consistent estimator of population mean. So sample mean is both unbiased as well as consistent estimator of population mean. Okay. Actually, in one of the previous lectures, I mean, in yeah. So I discussed this one. I derived that expected value of sample variance. It is actually 1 minus 1 by n sigma square. Now, again, as n tends to infinity, n tend to infinity, what will be this term? It will be tending to 0. So what will be this term? It will be tending to what? Sigma square. So as our sample size grows, our expected value of S square, it also start tending towards sigma square. Okay. Now, suppose this question is your exam for 5 or 10 marks, what 5 marks, okay, whatever mark. Okay. Then how will you prove this? That if we are taking a sample from normal population whose mean is mu, variance is sigma square, sample mean is consistent estimator of population mean. Actually, there will be no change in the proof. Why? When I proved this one, just we have proved that sample mean is both unbiased as well as consistent estimator of population mean. We didn't assume any distribution for the population. When we have proved this, okay, we didn't assume that our population is having normal population or Bernoulli population or any population. Okay. So, okay, one thing here, I have already, please mind that many, actually these lectures are in series. So if you feel that something I am discussing that is new to you, please once again go back to the previous lectures because I have already stated that usually the distribution of population is known. Okay. So here, if the, and what's the meaning of this that I have already discussed. So whether the sample is from normal population or it is from Poisson population or any other Bernoulli population, sample mean, it will always be consistent estimator of population mean. So if this question is an exam, actually, how many things you will prove, it will depend upon its marks. Suppose it is of 10 marks, then you will prove that expected value of xi is mu. Okay. Then you will prove that expected value of x bar is also mu. Okay. So from here, you will write this thing that expected value of x bar, it approaches to mu as n tends to infinity. Then you will prove that variance of x bar, it is sigma square by n. Okay. And obviously it approaches to 0. So obviously the number of steps in our proofs, it will depend upon the marks of the question. But no matter from whatever population our sample is coming. Okay. So whether it is normal population, Bernoulli population, Poisson population, sample mean is always a consistent estimator of population mean. Okay. Now, invariance property of consistent estimator. Actually, what is the meaning of invariance? Invariance means not changing, remaining same. Okay. So Tn is a consistent estimator of gamma. It is given that Tn, CE stands for consistent estimator. Okay. Then if Tn is consistent estimator of gamma, then this property says psi of Tn, the psi of Tn, it will be consistent estimator of psi of gamma. If, wait, if Tn is a consistent estimator of gamma, okay, then psi of Tn, it will be consistent estimator of psi of gamma. If you look carefully, if I operate on both sides, gamma, okay, so actually if I'm operating gamma, actually I am making the argument. I am making both sides the argument of psi. The both side, and actually this is called the argument of the function. Okay. So if I am operating psi on both sides, okay, the consistent estimator property, it remains same. Okay. Now this psi, it must be a continuous function. Please mind. This property doesn't hold for any psi, any arbitrary function psi, but this psi, okay, it should be actually, we can write that this psi, here you can write psi. Actually, here it can be function of any variable. It may be function of x, it may be a function of y, z, whatever, where this psi, it must be a continuous function of that variable. Okay. Now, uh, suppose psi x, it is say 2x square minus 3x, and psi y, say it is e raised to power say minus 4y, and psi of z, for z or z, say it is sine of say 2z square minus or plus 3z. Okay. Now, algebraic function, polynomial function, exponential function, sine function, cosine function, they are continuous everywhere. Okay. So means on the whole real line. And tangent function means tangent function, it is not continuous everywhere. Actually, tangent function is discontinuous at pi by 2. So since these functions, they are continuous everywhere. So for these, we can apply this property. How? Suppose Tn is consistent estimator of gamma. It is given. Suppose Tn is consistent estimator of gamma. Then this property says psi of Tn. So what is psi of Tn? Psi of Tn. It is 2Tn square minus 3Tn. Because if this function, it is function of x, psi of x. So what will be psi of Tn? It will be nothing but this. Okay, then this one, it is consistent estimator of what? Psi of gamma. The psi of gamma. Now, what is psi of gamma? So, obviously, it is 2 times gamma whole square minus 3 times gamma simple. Okay, because once again, if this is the psi of x, this will be the psi of Tn, and this is the psi of gamma. Again, suppose Tn is consistent estimator of gamma, and this is our psi, which is a continuous function. Then, what is psi of Tn now? It will be e raised to power minus 4Tn. And this will be, okay, this will be consistent estimator of what? Psi of gamma. And what is psi of gamma? It will be e raised to power minus 4 times gamma. Done. And once again, suppose Tn is consistent estimator of gamma and psi is this function, and even it is continuous function. So what will be psi of Tn now? It will be sine of 2Tn square plus 3Tn. And this will be consistent estimator of what? This will be consistent estimator of sine of, wait please. Yes, of sine of 3 gamma. Okay. this and plus 3 of 3 into gamma theta done. Okay, so this is psi of Tn. This is psi of Tn. Okay, and this is psi of gamma. Done. So this is the meaning of invariance property of consistent estimator. Now, once again, we have a sample, okay, that is taken from Bernoulli population. Actually, here the sample observations, they are capital Xi, capital X2, capital Xn. So I already stated that usually, not always, our sample observations, they will be by small Xi's. Okay, so this is one just case that here the sample observations are capital Xi's, but there is no confusion because here it is clearly stated that these capital Xi's are our random observations, means these are our sample observations. Okay, and this sample, it is taken from a Bernoulli population. How we know? Because these sample observations, either they can take the value 1 with probability P, success. Okay, means if Xi takes the value 1, then it is success. And it is taking the value 0, that is our failure with the probability 1 minus P. Then we have to prove that this one, obviously it is our Tn, which is a function of sample observation. It is a consistent estimator of this parameter. Here, what is the parameter? P. Okay. P is the probability of success. So here P, it is the probability that Xi, either you say capital Xi, okay, it takes the value 1, or you may say that this Xi, okay, means the sample observation, it takes the value 1. Okay. We need not to be much fussy about this. Now, suppose if in this one, if I multiply this by 2, okay, okay, rather than this here, wait, please. Oh, sure. Yeah. Suppose I make it a square here, okay, and here I write 2 and here it will be 3. Then what change will be here? Even here it will be p square, it will be 2 and minus 3p, okay. And similarly, suppose if I make plus here, then it will be plus here. Why so? This we will see how. Now, uh, there are multiple ways to prove this result. Actually, first of all, we will prove summation xi by n. This is consistent estimator of P. We will prove this thing. You can very well see. I clear this. Okay. Yeah. At first, we will prove that this summation xi by n, you can see the position. Please observe the position of summation xi by n. At first, we will prove that this summation xi by n, it is consistent estimator of P. Then by invariance property of consistent estimator, psi of summation xi by n, it will be consistent estimator of psi of p. Okay. Uh, where what will be our psi function? What will be my psi of say y? It will be y into 1 minus y. Because if this is my psi function, psi of y, what will be psi of this? Summation psi xi by n. Nothing but this. What will be summation psi of p? It will be nothing but this. And now I think my that remark is will be clear that if I write summation xi by n whole square and here say 2 minus 3 summation xi by n. Okay, so this will be consistent estimator of what? Which parameter? P square 2 minus 3p. Okay, because in this case, I will define my psi function, psi of say z, as z square or z square minus 2 minus 3z. Why? If this is my psi of z, what will be this? Psi of xi minus n. And what will be this? Psi of p. Okay. So here I think my point is clear. Now, in order to prove this thing, that summation xi upon n, this is consistent estimator of p. Mm, Multiple ways are there. Observe that this summation xi by n, what is this? It is x bar, sample mean. The sum of the sample observations divided by number of sample observation. Okay. And we have already proved that x bar is a consistent estimator of p, mu, population mean. This we have already proved. Okay. Now, here, what is this mu? The population mean. This mu is population mean. And here, population mean, it is nothing but p. It is nothing but p. Why? Because here our population is Bernoulli population. Here our population is Bernoulli population because every population unit, either it can have value 1 or 0. Okay. So for Bernoulli population or Bernoulli distribution, what is the mean? It is P. Why? Because if X is having binomial distribution with parameter n and p, then what is its mean value? Means what is the mean of X or the mean of binomial? Binomial. It is NP. Okay. And I have already mentioned that if in binomial distribution your n is 1, then your binomial distribution becomes Bernoulli distribution. So if your x is having Bernoulli distribution, okay, here x is having binomial, but if x is having Bernoulli, it is having Bernoulli distribution, then what will be the expected value, mean of x? It will be simply p, okay, because what is n? 1, okay. This is the mean of binomial distribution, and this is the mean of Bernoulli distribution. Even this fact I have discussed in previous lecture. Please do watch that. Okay. Now, so what is this P? It is the mean of Bernoulli distribution, expected value of X. So we also say what is mu? It is also the mean of the distribution. And obviously here our distribution or population is Bernoulli. Okay. So what should be this P? This P is nothing but mu. I repeat, this symbol mu we use for what? Wait, please. Yeah. This symbol mu we use for population mean. And here, what is your population mean? P. Why? Because your population is having Bernoulli distribution. Okay. So for Bernoulli distribution, the mean is P. Okay. Since here mu is P, so you will write that X bar is a consistent estimator of P. Okay. So what is X bar? It is nothing but summation Xi by N. Okay. And since this is consistent estimator of P, so then you will write that by invariance property of consistent estimator psi of this will be consistent estimator of psi of P, where what is your psi? Psi is this function, which is a continuous function. This is a continuous function of y. Why? Because it is a polynomial function, polynomial or algebraic function of y. Okay. So this is one way of proving this. So if you are trying to prove this result by this way, so first you will prove this result. So for that, once again, you will prove that expected value of xi, it is mu. Then expected value of x bar, it is mu, and this will imply expected value of x bar, it tends to mu as n tends to infinity. Then variance of x bar, it is sigma square by n, and obviously this will tend to 0 as n tends to infinity. So you will prove these, and once again the number of steps in all your proofs, it will be dependent upon the marks of the question. If it is of 10 marks, the steps should be more. If it is of less marks, steps should be less. Okay. So it tends to infinity. So it proves that x bar is consistent estimator of mu. Then you will write, you will mention that here mu is nothing but P. Okay. There is no need that you should write in that much detail. You can simply state, since here mu represents population mean, and since here population follows Bernoulli distribution, and for Bernoulli distribution, the mean is P. So that's why here mu is nothing but P. Okay. And what is P here? It is probability of success. Okay. And Bernoulli distribution I have discussed in the previous lecture. Please do watch that. Okay. So after that, you will write that by invariance property of characteristic estimator, this will be a consistent estimator of this, where psi is this, which is a continuous function of y. Okay. Now, there is another way to prove this result. Just wait, if I can check out that, please wait. Mm, just give me some time, please. Yes. This is the another way to prove the same result. Now, what are these xi's? They are Bernoulli variates. Why they are Bernoulli variates? Because either they can take the value 1 or 0. Now, what is this thing? Actually, here it should have been, if he is using capital Xi, so even here it should be capital Xi. Okay, so here it should have been capital Xi. So what is this? This, it is the summation. It is the sum of n. It is the sum of n independent Bernoulli variates. Okay, so what is the meaning of IID? Its meaning is that they are independent and identically distributed. They are independent and identically distributed. So this IID, this is a standard short form in uh, statistics. I stands for independent, and this I identically. So these sample observations are independent, and what's the meaning of identically distributed? Means all these xi's, they have identical, same. They have identical or same distribution. Okay, so actually all these sample observations, they have Bernoulli distribution. Okay, so what is this summation xi? It is the summation capital Xi. It is the sum. It is the sum of n independent Bernoulli variates, and this will be nothing but a binomial variate. Even this remark I have discussed in previous videos. So, what will be expected value of T and P variance will be this. So, what is X bar? Okay, so actually this quantity, if you recall back, X summation Xi by n, it is our sample mean, which is T by n, obviously, because this is your T. Now, what is expected value of X bar? It will be expected means you take on both side. On both side, you take expectation. Okay, because what is your X bar now? It is T by n. And on both side, what do? You take E, expectation. Okay, so what will be this thing? What will be this? It will be nothing but 1 by n expectation of t. And what is expectation of t? It is np. And n cancels and it is p. And this is the same result which I discussed in the previous uh, means in the first method, that what is expected value of x bar, sample mean. It is population mean. Yes or no? And here what is our population mean? P. Okay. So now, what is variance of x bar? Variance of t by n. Okay. So here, instead of expectation, what will you do? You will take variance on both sides. You will take variance on both sides. You can see very well. Okay. So if you take variance of x bar and variance of uh, t by n, this is now 1 by n square variance of t. And what is variance of t? npq. Variance of t is npq. Okay, why? Because t is a binomial variate. And n cancels, so it is pq by n, which tends to 0 as n tends to infinity. Okay, so even it is giving us the same thing. Why? Because in the first method, I use this, that what is the variance of, wait, yeah, what is variance of sample mean? It is sigma square by n. Okay. And what is sigma square here? Population variance. So what is the population variance here? PQ. Because what is the population, what is the variance of binomial distribution? Variance of binomial distribution. It is NPQ. Okay. But here, since it is Bernoulli population, and in Bernoulli, what is N? 1. Okay. So here, what is the population variance? It is PQ. Just like what is the population mean is P. Okay. The population variance is PQ and divide by N. So again, actually, this is giving us the same result. But the only thing here, there is a certain change in symbols, but ultimately they are same. So uh, since this expected value of sample mean, it tends to P, variance tends to 0 as sample size becomes sufficiently large enough. So X bar is a consistent estimator of P. And now this one, it is being a polynomial in X bar. Okay, this function, okay, or this function, which is a continuous function of X bar. Okay, so since this is a continuous function, so x bar is a consistent estimator of P. So by the invariance property of consistent estimator, this function, it is a consistent estimator of this one. Okay. So obviously, what is x bar here? This is nothing but summation xi by n. So here it is 1 minus summation x I by n. Wait, please. So this will prove that this estimator, okay, it is consistent estimator of this parameter. Okay. So thank you. Just wait. There is a